So, and now we have the WAS speaker. So the WAS presentation is on investigating dynamic routing in tree-structured LSTM for sentiment analysis. And the presentation is going to be done by the first author, Jim Wang.
Hi, everyone. I have noticed a lot of people has gone to Disney Resort, so we got hurry. I am Jin Wang from Yunnan University. My presentation here is investigate dynamic routing in tree-structured LSTM for sentiment analysis. Okay, here is our outline. In sentiment analysis, the sequential neural network, such as recurrent neural network, gated recurrent units, and long short-term memory, are commonly used due to their ability to capture long-distance dependency in sequential text. However, this model belongs to BIOS model, where the word in the tail of a sentence are more heavily emphasized than those in the header for building sentence representation. For example, the priority for each word vector will be fantastic, really, is, story, this. This prioritization seems satisfactory for this sentence, but note that the key component could appear anywhere in the sentence rather than necessarily at the end. Previous work proposed tree LSTM model to introduce useful structural information from sentence parser trees. However, the tree LSTM also heavily emphasized the root node in the tree to build sentence representations. That is, words that are close to the root will be given higher priority than words that are far away from the root. The tree LSTM still could not avoid the BIOS problem because the node, for example, fantastic, that contribute more to the prediction, but lies in the leaf node at the bottom of the tree. So to deal with this issue, we often use self-attention. Self-attention is an self-attention is another commonly used method to automatically learn the contribution of each hidden state and assign more weight to those words with higher contribution. By using a softmax function, the self-attention can calculate the weight for each hidden state and word. So here is our model. There are three components in our model. First, the given sentence is parsed as a tree-structured, and the tree LSTM is used to produce presentation for representation for all non-leaf nodes. The vector representation of this sentence is then generated by composing the word vector of all non-leaf nodes in the tree according to their weights learned by dynamic routing algorithm. Finally, the composed sentence vector is used for sentiment prediction. Differ from the sequential LSTM, in tree LSTM, the hidden state and memory cell of the non-leaf node is a composition of its left and right child. The input gate, output gate, and the forget gate are similar as the sequential LSTM. After that, we use dynamic routing on all hidden state of non-leaf nodes to generate the sentence representation. The first step, the input capsule H head is obtained from HT with an inner transformation. Then VG is awaited sum over all H head. The output capsule SG is produced from a non-linear function from VG. The coupling coefficients CTJ are are determined by iterative dynamic routing process from both BIG. The updated information in BTG comes from the Scala product from the Scala dot from the H head and the SG. So in experiment, we use two datasets for evaluation, including both classification on SST and regression on EMNLP for valence arousal prediction. The valence here refers to the degree of positive and negative sentiment, and the arousal refers to the degree of calm and excitement. Both valence and arousal are real value. So we compare our model with several deep neural networks, including CNN, GRU, LSTM, and tree LSTM. For the sequential models, we additionally implement enhanced version, use a bidirectional strategy and a two-layer stacked architecture. To investigate the performance of self-attention, we also implement attention by LSTM, attention by GRU, and attention version tree LSTM by taking as input the hidden state of all non-leaf nodes into self-attention layer. The matrix here for SST, the matrix is accuracy for both binary and fine-grained classification. For emotion bank, we used the Pearson correlation coefficient. So for SST, both the enhanced bidirectional and the two-layer GRU LSTM outperform the standard GRU LSTM, and the tree LSTM with structured information achieved better performance than all of them for both classification and regression tasks. Once the dynamic routing algorithm and the self-attention was introduced, the attention model and the capsule tree LSTM further improved the performance of tree LSTM. The capsule tree LSTM outperformed attention tree LSTM about 3.2% on classification and 3.1% on regression. So we also analyzed the effect of dynamic routing. The test sentence was first divided to several groups according to their dips in the parser tree. For example, the dips of the example sentence in previous is 3. The performance improved of capsule tree LSTM over over tree LSTM was then calculated for each group. The results show that the performance increased with the increase of the dips. The reason is that the tree LSTM may suffer from more serious bias, a problem for sentence with a deeper tree structure because the useful nodes in the deeper levels tends to be ignored. Conversely, the capsule tree LSTM can assign higher weight to the nodes that contribute more to the prediction, even though they lie in the leaf node at the bottom of the tree. We also compare the dynamic routing and the self-attention. The dynamic routing can extract key information by making agreement between the input and output capsule. Such a reweight mechanism is somewhat like self-attention. However, here we also present more detailed analysis on the difference between dynamic routing. The self-attention used a fixed policy to learn the weight for hidden states and does not take the final output representation into account. In dynamic routing, the input capsule is employed to calculate the coupling coefficient as a weight vector to the output capsule. It leverages both information from input capsule, input hidden states and output label to get more accurate weight to extract the input information. Okay, in this study, we present a capsule tree LSTM which use dynamic routing to automatically learn the weight of each node to compose sentence representation. In the future, we try to automatically find the convergence of the dynamic routing and conduct more detailed analysis to continue enhance the proposed method. Okay, thank you for your listening.
Thanks for the interesting talk. Any questions? No questions? Okay, I have a question. So what I find strange is that you don't compare anywhere in your results to kind of transformer-based models like BERT. It has been argued that they can learn those kinds of structures, especially if the sentence is not very deep. I mean, would they be able to find those kinds of associations? There has been like some blog posts that were trying to explain what BERT actually does, and they have been like trying to say, okay, maybe it learns something similar to trees at the end of the day. So, any thoughts about that?
Yeah. We don't compare with any transformer because the most issue we deal with is the resigning weight problem. So the most model we want to compare is SelfAttention. So we want to deal with the problem that SelfAttention does not consider the output in the architecture. So we want to use dynamic routing to iteratively learn the weight from the input hidden state and the output from the labels.
Right, but I mean, why is this not in principle applicable to transformers, which also have input states and also have output states and also have attention? So, I mean, can't you have there some attention matrix that is informed by the ways that you are learning to kind of learn to pay more attention to certain structures and kind of less to others?
Sorry, pardon?
So I mean, I'm saying kind of why in principle this cannot be applied to a transformer. That's the short question. Because it's also attention based.
I'm sorry.
Okay, other questions? Yes.
Hi. Can you comment on the number of iterations in your dynamic routing and the performance?
For both SST and EMO-Bank, our best iteration is 3. We use the grid search process to decide the best iterations. By far is 3. Yeah.
Okay. Thank you very much.
Okay.
Okay. Other questions? No questions? Okay, let's thank the speaker.
Okay, thanks.
And this concludes our session. So there's some other session and there are also buses, and then it's your choice what you do. You go to Disney or you see more posters and another session.